So today we're going to talk about histograms, and if you remember from last class, we were talking about frequency distributions. So the key concept, a frequency distribution is a useful tool for summarizing data and investigating the distribution of data. An even better tool is a histogram, which is a graph that is easier to interpret than a table of numbers. A histogram is very good for people who like visual representations. It's a clear graph, usually easy to read, depending on how people set up their x-axis and all of that. We'll take a look. So a histogram is a graph consisting of bars of equal width drawn adjacent to each other, unless there are gaps in data. So we talked about gaps the other day, and remember, there are only gaps if there is a zero frequency. So the horizontal scale represents the classes of quantitative data values, and the vertical scale represents the frequencies. The height of the bars correspond to the frequency value. So, histograms are a graphic version of a frequency distribution. So, if you look at the left, you see that is our frequency distribution that we talked about last class, and to the right is the histogram that shows that information. So, if you see how the class 60 to 69 on the histogram on the x-axis, you see it's a 59.5 and 69.5, and that's where what we use for the edges of our bar. Then that's what we call our class boundaries that we talked about when we were doing frequency distributions. Now, if you notice between the 109.5 and 119.5, you see a gap. That's because there were zero pulse rates that fell in that region. So if there's any gaps between the bars, that means there was a frequency of 0. Otherwise, the bars touch each other. And so you can easily look at this and see the difference in each region. And you could tell like which class had the highest frequency. It's just a lot easier to look at. So the important uses of a histogram is that it visually displays the shape of the distribution. We're going to talk about different shapes in a minute, and I don't mean like circles, rectangles, triangles, but you'll see. It also shows the location of the center of the data and how the data is spread. You also can identify outliers. So if you were to have several gaps and then ended up with one frequency, you would see that on the histogram, you would have a lot of space between bars. So now, if you remember, we talked about relative frequency distributions. You can also have a relative frequency histogram. What's different is if you look around along the vertical axis, that instead of having the actual numerical frequency, you have the percents. And so it would go along with a relative frequency distribution. So the horizontal axis is the same. You have your class boundaries are the same. The way that it looks is the same. The height of your bars. You can still see that there's the gap for the 110 to 119 class. So just notice that the histogram will look the same, but your vertical scale will match the relative frequency with the percent instead of the actual numerical. So, some critical thinking interpreting histograms. You can see the center of the data, the variation, the shape of the distribution, whether there are any outliers, and time. So those are some of the things that we were talking about. And now, the shapes. So when I talk about shapes, it's how the data is shaped is what we're talking about. So if you look in the yellow, the bell shape, kind of looks like what we think of when we think of the bell curve with a normal distribution. And so right there, you see the mode, what occurs the most would be that the highest bar that's right there in the middle. And then it's very symmetrical with how it goes down to the left and towards the right. In the middle, you see bimodal. It's like two little bell shaped put together is kind of how I think about it, because you have two modes. There are two bars that have the most frequency. Excuse me. So, what I see people have the most trouble with is the skewed right and skewed left. So the skewed right, also sometimes called right tail, the majority of your frequency is to the left, and then like the tail of it comes off to the right. Similarly, skewed left, the tail goes off to the left if you look at it that way. The highest frequency, though, is actually to the right. So just make sure you pay attention to the skewed right and skewed left, because those are the two that people mix up the most. Now, if you look at uniform, you might notice overall there's no big change in the frequencies. Everything's about the same. Then random, you can't really say anything specific about it. It's just random. There's all different frequencies that doesn't go in any type of pattern or any way to classify a specific shape. So, we will talk a lot about normal distributions throughout the semester. So, because the histogram is roughly bell-shaped, we say that the data has a normal distribution. And so you see, in this one, the histogram's not perfectly symmetrical, but overall, it fits pretty nicely to that bell curve. Skewness. A distribution of data is skewed if it's not symmetrical and it extends more to one side than the other. So skewed, if you think about what you see here in the green and the purple, skewed to the right, the tail goes off to the right. Skewed to the left, the data falls off to the left, the frequencies. So data skewed to the right. You see it goes down to the right. It has a longer right tail. So that's kind of how you can remember it. Skewed right has the longer right tail. Skewed to the left, the longer left tail. So, assessing normality with normal quantile plots. Normal distribution. The pattern of the points in the normal quantile plot is reasonably close to a straight line, and the points do not show how the systematic pattern that is not a straight line pattern. So, it's not a normal distribution. The population distribution is not normal if the normal quantile plot has either or both of these two conditions. The points do not lie reasonably close to a straight line. The points show systematic pattern that is not a straight line. And so when I think of this, I think about a line of best fit. And so when you have a scatter plot, if you're able to draw a line and most of the points are around that line, I think of it as kind of like a median line where that line goes in the middle of the data, then it can represent a normal distribution. Now, it's not a systematic pattern. It doesn't have some type of specific pattern to it. This right here, not a normal distribution because this is not kind of like a median line. If you see all of that, the frequency, all that data to the left, and that line isn't like centered towards the data. This one's a little bit harder to understand because you might be like, oh, well, all the points are surrounding it. However, this is a very systematic pattern, so you wouldn't call this a normal distribution. So for your homework, you read chapter 2, section 3 and 4. Make sure, I would go at this point and make sure you've read almost all of chapter 2. And we will follow up with graphs that enlighten and deceive next class.